Hey everyone, welcome to GemChem. Now today we are going to learn about carbon-carbon single bond formation. This is mainly based on chapter alkanes. Now in this first video of alkanes, we will learn about general formulation and methods to prepare alkanes. Now let us start today's video. Now what is the general formula for a alkane, which is linear in shape? Now CnH2n plus 2. So suppose if we take n equal to 1, then we get CH4, that is methane. If n equal to 2, we get this as C2H6, which is ethane. And for cycloalkanes, that is CnH2n, so 2 hydrogens short. So this cyclic alkane can only be formed when it can join. So the least carbon containing cyclic alkane is cyclopropane. So it has the formula of C3H6, that is 2 hydrogens here, 2 hydrogens here, and 2 hydrogens here. Now alkanes chapter has a part of nomenclature. So nomenclature of alkanes is already shown in IUPAC nomenclature part 2 video. Link will be given in description box. Do watch it, it will be helpful. Now we will learn about the general method of preparation. The general method of preparation are, which we will learn in this video, is heterogeneous hydrogenation, which occurs with the help of catalyst, reduction of alkyl halides, catalytic hydrogenolysis using Grignard reagent, decarboxylation, WURTZ reaction, and Core-House synthesis. Now let us see first method, that is heterogeneous hydrogenation, which is reduction of unsaturated hydrocarbons. Now heterogeneous hydrogenation, formerly it was occurring with nickel catalyst. Now the nickel catalyst was prepared by reducing with hydrogen nickel oxide, which deposited on a suitable inert porous support. That porous support was known as Kazal-Gohar. For example, this reaction, see, we have taken a alkane. This one we know it to be as ethene molecule, which on reacting with hydrogen forms ethane. That is, one hydrogen gets attached to this part. That is CH3 refers to that CH2 attached to H for one bond, and here CH2 attached to H. So there is a formation of alkane. Now this alkane formation can take place in presence of different catalysts. First catalyst is nickel. This is most primitive one, but after some times this nickel was discarded and we started using Raney nickel. Now how Raney nickel is prepared? Now Raney nickel is basically an alloy containing equal amounts of nickel and aluminium digested with NaOH. Now when it is digested with NaOH, this aluminium dissolves and the residual is finely divided nickel, which is then washed and stored under water or ethanol or other liquids. Now this is usually very effective for lower temperatures and is more reactive than the nickel catalyst. Reaction can take place also at room temperature. Now another catalyst which is used is Adams catalyst, that is PtO2. Now this is prepared by reducing platinum oxide with hydrogen before the compound to be hydrogenated is added. So PtO2 with hydrogen forms this catalyst, and then this ethene is added to the pot. Now the other two are palladium black, that is, it is a transition metal, and many platinum metals can also be used as catalyst. Pt, Pd, Rh, Ru, that is platinum, palladium, ruthenium, rhodium. Now, many organic compounds are reduced by passing their vapors mixed with hydrogen over nickel and heated at 200 to 300 degrees Celsius. This method is known as Sabatier-Sanderson's reduction. Now, ranni-nickel is more effective than supported nickel catalyst and is effective at lower temperatures and often at room temperature. Now, how this heterogeneous hydrogenation occurs basically. If we consider an alkane molecule, suppose this one, it will have a p orbital which forms a double bond. Now these p orbitals approaches the catalyst surface containing the hydrogen. Okay, now when it approaches the catalyst surface containing the hydrogen, it attaches with these hydrogens and forms bonds. So, the p orbital of this carbon and the s orbital of this hydrogen forms a bond. They come near to each other to form the bonds. This carbon and suppose this carbon forms a bond with this hydrogen. So, they form a bond. This bond, which was a pi bond, this bond breaks up to form a bond between carbon and hydrogen. Now, the situation is like this. Here there is hydrogen, here there is hydrogen, another hydrogen is in this surface and this surface, and we get other two hydrogens from the catalyst surface. So hydrogenation takes place from the same surface. This is important to understand. Now we will come to our next method of preparation by reduction of alkyl halides. Let us see. Now, this reduction of alkyl halides can take place in two ways. One, using dissolved metals, that is, the metals are dissolved in different solvents. Now, basically we use zinc as metal, zinc plus acetic acid or HCl, or zinc in NaOH, or zinc copper couple in ethanol. There is electron transfer from metal to substrate followed by addition of proton from solvent. Now, we see that zinc forms Zn2 plus 2 electrons, that is, it gives up 2 electrons. One of these electron is given to Rx, that is our alkyl halide. X is halogen here, any kind of halogen, chlorine, bromine, iodine, fluorine. Now after taking up one electron, since X is electronegative, that is, it is electron lover, so it will take up one electron. So the bond breaks like this. That is, it will break like this. When it breaks like this, one electron remains here and one electron remains here. So one electron X has and another electron comes from E. So it has two electrons. Negative sign refers to 2 electrons. So now X has 2 electrons and R has 1 electron, so it is a radical. Now this R takes up another electron to form R minus. That is, it is having 2 electrons. Now when ethanol is added, that is the solvent is added, this R minus attacks this hydrogen and this hydrogen gives up electron totally, that is 2 electrons present in the bond to C2H5O, and this gets bonded to the alkyl group, that is RH group, and this forms the alkane, and C2H5O minus stays as it is. Again some proton comes and ethanol is preserved in its own form. Let us see another example for this case. See, there is 2 chlorine. So zinc here with another solvent, any kind of solvent if given here, then these two parts join together. One hydrogen comes from here and another comes from here and that joins together. Here there is solvent. This solvent provides hydrogen for this, and here the negative charge, when it comes, it attacks this one and this chlorine gets away. So we get a cyclic alkane, that is cycloalkane. The formula for this is C5H10, that is CnH2n. Easy? because 5 carbons, so we get also the chemical formulation. Now we will see how the reduction takes place of alkyl halides using reducing agent. This is important. Now the reducing agents used are lithium aluminum hydride, NaBH4, PH3SNH. So these reagents have different properties to reduce different kinds of alkyl halides. Now see, 1 degree and 2 degree alkyl halides are reduced by lithium aluminum hydride, and 2 degree and 3 degree are reduced by NaBH4, and 1 degree, 2 degree and 3 degree are reduced by PH3SNH. Now important thing is that they have different kinds of selectivity for different kinds of reagents, but the substrate is same, that is alkyl halide. So why this is so? We have to know the mechanism for answering this kind of questions. Now before answering, we have to also understand what is 1 degree alkyl halide, what is 2 degree and what is 3 degree. So let us see what is it. Now if a carbon is attached to another carbon and hydrogen and a functional group, then this carbon is 1 degree. That is, it is attached to another one carbon. So 1 degree. If a carbon is attached to 2 carbons and hydrogen and a functional group, then it is a 2 degree carbon. And if the carbon is attached to 3 carbons, no hydrogen and an X, it is a 3 degree carbon. So this is how we determine the carbon to be 1 degree, 2 degree or 3 degree. Now we will understand the mechanism for this. Now how to understand this mechanism? Let us first see the reactions. Now we see that lithium aluminum hydride can only reduce 1 degree and 2 degree. Rx lithium aluminum hydride, that is this 4 comes here, and it forms an alkane. Similarly, NBU3SNH, that is a tin reagent, it also forms the alkane in presence of HNu, that is light. Now why these reagents have different selectivities? That is important to understand. Now how do lithium aluminum hydride react? We have to see this. Lithium aluminum hydride can be written as a lithium plus and AlH4 minus, right? So AlH4 minus can also be written as like this, Al, H, H, H and H, right? So this negative sign, it will be present because aluminum has 3 bonding pair of electrons and this is the excess one. So it will try to become neutral. So it will give up one hydrogen to become neutral. Thus we get this one as our alkyl halide. Now we see that this hydrogen leaves and attacks the carbon from the back side. There is an SN2 attack. Now this X leaves and it goes to lithium plus. So we obtain the product as H, C, and there is an inversion of configuration as it is an SN2 attack to form this one, right? And lithium halide plus AlH3. So we see, since there is an SN2 attack, so 1 degree and 2 degree is alkyl halide reaction is supported, but 3 degree becomes a bulky group, right? Since it is a bulky, so backside attack becomes difficult. So we only observe reduction of 1 degree and 2 degree alkyl halide. Now we will see the mechanism for NBU3SNH. Here basically the reaction takes place in a radical pathway. Since we see HNu, so it basically indicates a free radical mechanism. Now NBu3 SNH on providing light produces NBu3 SN dot. Now this SN dot from Rx plus this radical forms R dot radical, and this X, that is this X, gets bonded with this NBu3SN. So we get NBu3SNX. Now we have R dot and we have the NBu3SNH. So R dot plus NBu3SNH. This SNH gives away its hydrogen just like here it has given to give RH, and again this radical is regenerated here. So this is the mechanism of NBu3SNH. So we can understand from this mechanism why it supports all kind of alkyl halides, because there is no backside attack, no problem for bulkiness, so it can react and reduce any kind of alkyl halides. Now we will see our third method, that is catalytic hydrogenation. This is another method in which alkyl halides are reduced using hydrogen. Now hydrogenation, this is catalytic hydrogenolysis, right? So what do we mean by hydrogenolysis? We see a word hydrogen and lysis. Hydrogen comes from the addition of hydrogen and lysis refers basically to a breakage, right? So hydrogenation in presence of catalyst accompanying the breaking of bond using hydrogen. This is known as hydrogenolysis. So here Rx plus H2, palladium carbon as the catalyst, produces RH plus HX. Now see, this Rx bond breaks up and hydrogen adds up, whereas this X attaches with HX. So we see two things, that is breakage of bond and formation of this by addition of hydrogen. Clear? Now this process is very much favored if this R group is a phenyl ring and this X is present in a benzyl position. X can be taken as halogen or OH or NH2. Now this is an important fact, 1 degree, 2 degree chlorides and bromides are not affected in neutral and acidic media. If we take 1 degree or 2 degree chlorides and bromides in neutral or acidic media, this reaction does not occur. For 1 degree, 2 degree, 3 degree iodides and 3 degree chlorides and bromides, they are easily converted to alkanes. Now let us see our next method. Now this is a Grignard reagent method. How this occurs? Now alkyl halides in ether reacts with magnesium to form alkyl magnesium halides or Grignard reagents, which on treatment with water or dilute acids are decomposed to alkanes. Now we see an alkyl halide which reacts with magnesium. Now there is an insertion of magnesium in between these two. So this magnesium gets inserted. When water, that is basically a proton source, comes, then R attaches with this proton source, leaving behind MgOH whole X. This is another method. Now we will see another method, that is decarboxylation. This is a primitive method and we all know it. Just a revision for this case. By heating a mixture of sodium salt of carboxylic acid and soda lime, we get this. Soda lime is NaOH CaO. RCO2Na, we get a sodium salt of carboxylic acid and react it with NaOH CaO. We get RH and Na2CO3. By heating this, heating prefers decarboxylation. But in all cases decarboxylation is not possible. We will also see this in later cases. Now let us see KOLBE'S electrolytic method. Now this is a method of electrolysis by which two mixture of carboxylic acid salts are taken and they are coupled together. But this method C, that is RCO2K plus R2CO2K plus 2 water produces this. This is the product desired, plus 2 carbon dioxide plus H2 plus 2 KOH. But from this we also get this product, that is self-coupling, RR and R2R2. These are not at all desired. But why do we get such products? Because this reaction takes place through radical pathway, and we will see the mechanism. So if radical pathways occurs, we will get R dot and R2 dot, right? They can self couple also, or they can interchange within themselves also. So we get three kinds of product, this and this one. So it is a drawback, but we have to know the mechanism also. It's several mechanism has been proposed for this reaction. The free radical theory is one favored and strong to be supported. Now we will see for sodium propionate, that is with 3 carbon atoms, 1 CO2 group in each of them. When sodium propionate is electrolyzed, we get N-butane, ethane, ethylene, ethyl propionate. These are the different kinds of products obtained. Now let us see the mechanism. Now what is sodium propionate? That is C2H5CO2K. Now this basically can be represented as C2H5CO2 minus and K plus. Now minus, as we know, represents 2 electron. So C2H5CO2 minus can give up one of its electron to form C2H5CO2 dot plus 1 electron. Right. Now this C2H5CO2 dot can form C2H5 dot and carbon dioxide. This is possible by breaking the bond in between this. So one comes here, radical, another comes here. So this one pairs up. So we get neutral carbon dioxide and this one remains as free radical. Now we will see what are the products formed using this radical. Let us see. Now 2C2H5 dot basically forms butane, that is C4H10, whereas C2H5 plus C2H5 can undergo disproportionation to form a ethane molecule as well as a ethene molecule. So C2H6 plus C2H4. And another possibility is that C2H5 dot adds up with C2H5 CO2 dot to produce C2H5 CO2 C2H5. So this is how the reaction occurs. Reaction gives N-butane, ethane, ethylene by disproportionation and also ethyl propionate. That is, this product is ethyl propionate. Now we will come across WURTZ reaction. This is an important reaction. Now this is basically a reaction between an alkyl halide and another kind of alkyl halide in presence of sodium metal to form a coupled product, that is, from this alkyl group and this alkyl group a bond is formed between these two plus 2NaX, that is a sodium halide. Now it is found to give the best yield when this R and this R2 are the same, and the reaction generally falls with tertiary alkyl halides. There are two types of mechanisms proposed for this case. Now we should also know that WURTZ reaction is for alkyl groups, right? And we will come across WURTZ fatigue reaction. This WURTZ fatigue reaction is same reaction, but name fatigue comes from when aromatic halide that is containing a ring reacts with an alkyl halide. The reaction becomes WURTZ fatigue reaction. These two couples together to form this kind of product. So nothing different, but just the one of the substrate is a aromatic halide. Okay, now let us see the two proposed mechanism. See the mechanism with C2H5Br. Now see, this is the first mechanism, C2H5Br. There is a bond between carbon and bromine for this case, plus 2 sodium metal free radical. We get C2H5 minus Na plus, and another is NaBr. Now what is the case? The 2 electrons present here is completely taken by this, and this bromine attaches with one of these sodium, and these 2 radicals are attached here. So we get NaBr and C2H5 minus Na plus. This is a organometallic intermediate. The intermediate is an organometallic intermediate as it contains an organic part as well as a metal part, that is sodium. Now we will see the second step, that is C2H5 minus Na plus now reacts with another molecule of C2H5Br to form C2H5 bonding with another C2H5, that is it is forming the butane molecule plus NaBr. Right. Now this is the first mechanism which we have seen now. Now we will see the second mechanism. Let us see. Now second mechanism considers an intermediate which is free radical. Now we will see again by taking ethyl bromide, C2H5Br with one sodium metal free radical reacts to form C2H5 dot plus NaBr. Now what is the case in this? Here is a bond, this breaks up. One of the radical comes here and one of the electron comes here. This and this bonds together and this remains as it is. Now the second step is this C2H5 dot reacts with another C2H5 dot to form C2H5, that is butane formation. Now here in this case the intermediate is a free radical. Clear? Now in many cases these two radicals can undergo disproportionation. When they undergo disproportionation, we get ethylene molecule and ethane molecule, just like previous case for KOLBE'S electrolytic method. Now this would account for the presence of ethane and ethylene in the products. So we conclude that these are the drawbacks of these two methods and why these occurs, because of the placement of free radicals in different situations. Now we will see our last method, that is the Korehouse synthesis. In this Rx, that is an alkyl halide, gets substituted by a lithium to form a alkyl lithium compound, which on reacts with copper halide to form Gilman reagent, or most importantly lithium dialkyl copper reagent, which on reacting with an alkyl halide produces a coupled product. Now in this case the competitive reaction for this is basically an elimination. So we use a less hindered alkyl group in case of halide because backside attack takes place, and more hindered one taken as Gilman reagent, and this is important. Now let us see, if we try to prepare a molecule like this, CH3, CH2, CH, CH2, CH3, 3, CH3. and this one CH3. Now what kind of alkyl halide and what kind of copper reagent we should take? For this, generally we take the bulky group as the copper reagent. So we see this bond. Now this bond breaks as this. So we take this part as copper lithium reagent and this part as halide. Now what will be our substrate for this formation? We will take it as CH3, CH2, CH, CH3, whole 2, CuLi plus CH3, CH2, whole 4, Br. This is the most important reagent. We will find its use in every cases, mostly for organometallic compounds, and we will see it and deal with it later. But for this alkane chapter, this much is enough. Now let us see how to prepare this one. Again, we will cleave the bond, which is most of all in between the molecules. So we cleave this one. Now which is the bulky group? This is the bulky group we see. So we will take it as our copper lithium reagent, that is Gilman reagent, and the other part as our another halide, alkyl halide. So we take it as CuLi plus this part is taken as halide, right? Because less bulky. So this reagents are required for preparation of this alkane. That is, this is this one. We get this product. On using this reagents, we get this product. That is, this is our desired product. Now I am giving another question that will be helpful for practice. Now try to analyze the substrate used for making this particular alkane. So what are the starting materials? This is the question. So this much for today. Thank you for watching. Please do not forget to subscribe my channel for more videos and like, share and comment.